Okay, so today I posted the lecture notes from the last section earlier today, and we're going to be moving on to the next topic, which is divide and conquer algorithms. Do you remember that tomorrow you have your first quiz, which is in class, open book, open note, open computer if you wish, and it'll be written, so write some simple pseudocode to solve this problem, or analyze this algorithm, or something like that. It'll cover what we've covered this week, all right? And also remember that on Monday is your first homework is due. Now, the written portion, that's due in class. It needs to be up here physically on my desk so I can give it off to Garrett at the end of the day. But you have until midnight for the soft copy stuff. 1 second before midnight, by the way, according to the CSE clock. So midnight on Friday evening, you can have a few more hours to get the programs done. So keep that in mind. The physical copy, the written portions are due in class. The programs are due by midnight on Monday. Okay. So we've already seen the brute force algorithms, and they're generally inefficient because it has you essentially generating combinatorial objects, all pairs or all triples or all subsets or all permutations, right? These are exponential or super exponential algorithms. We did try to cut it down a little bit so that using pruning, right, we eliminated infeasible solutions. And then we backtracked and checked to see if there are other solutions. Even better, though, is to exploit some other structure to be able to produce even more efficient algorithms. In other words, not only can we prune out infeasible solutions, maybe we can also prune out other considerations. In other words, for example, like the all pairs are the closest two pair of points problem. Is there something there that we can exploit geometrically to cut down the amount of work that we actually have to do? So that we're going to look at a couple of these solutions that are all, basically divide and conquer, where you are, they're generally presented as recursive. Of course, that doesn't have to be that way. Any recursive algorithm can be rewritten so that it's not recursive. You can exploit a stack or some other data structure, and also any loop control structure can be rewritten as a recursive algorithm if you really want to. But they're generally presented as recursive solutions. You essentially cut the problem down. You cut it in half, or you cut it into thirds, or you cut out a chunk of it or something. And then on a smaller problem, and you cut that down until you get to a small enough problem that you can go ahead and directly solve it, or it's trivially solved. Once you've solved all these subparts, all these subproblems, you need to then combine the solution, because it might be the case where you've got this solution here and this solution here. You have to determine which is the best one, or you have to combine them in some way in order to solve the much larger problem that you cut down to begin with. And all along the way, you want to be able to exploit structure. Efficient algorithms are nothing more than recognizing and proving that a structure exists, and then exploiting that structure. Okay? So as a really quick review here, you have seen some divide and conquer algorithms before. In CS1, CS2, maybe even in 235. At least give me one divide and conquer algorithm where you're cutting the problem into multiple sub-problems, solving those problems, and potentially combining or merging those things together. What's one? Merge sort, right? Strong hint there, you're merging them together, right? You're taking an array and you're cutting it down into half, and you're going to sort this half over here and sort this half over here. And then once you've got those sorted, you combine them together by zippering them up, right? By merging them into one sorted array. And because this one is already sorted and this one is already sorted, you can exploit that structure and get away with only linear work, right? Another one would be binary search. So you're searching for a needle in the haystack. You look, you have a sorted array already. You jump to the middle, and you say, well, is the thing I'm looking for, is that equal? Oh, if so, then you're done. Otherwise, the thing that I'm looking for, is it in this half of the array, or is it in this half of the array? I'm exploiting structure. I'm exploiting the fact that it is sorted. And so I'm able to divide and conquer by saying, well, it's either in this half of the list or it's in this half of the list. I'm dividing it by throwing out half of it, and I'm conquering it by cutting it down and cutting it down and cutting it down until you get to one element, at which point it's trivially solved, right? So merge sort, binary search, and then I'd put quicksort in there as well, right? Quicksort is a divide and conquer approach because you choose a median, or you choose a pivot element, you put everything smaller over here, everything larger over here, and then you recursively solve this, you recursively sort this one, you recursively sort this one, right? So we're going to look at more problems along those lines. But before we do that, I want to get us back into the mode of thinking recursively. If you're actually going to, say, implement merge sort or quicksort or binary search, you'd probably want to do an iterative version of them instead. You can do, say just to pick on one, you can do a recursive version of binary search, but then you are exploiting the call stack. Whereas you could just get away with a simple while loop and two variables keeping track of the left and the right index. So it's much better in practice to forego recursion and get a non-recursive version of these things. But still, I want to think recursively because that allows you to think about dividing it. How do I divide it? How do I conquer it? By combining things. Okay? And thinking recursively, we're going to solve a problem that we already have solved iteratively. Right? We're going to solve linear search. We're going to have a recursive version of linear search. So given a collection A of n elements, A1, A2, ... AN, we want and a key element, K, we want to output true if A contains an element that matches it, contains K, right? You can think of these as numbers if it helps. Just think of them as integers, right? A collection of integers. And now if it were sorted, then I could go ahead and exploit binary search. I didn't put that condition on here. You could, of course, go ahead and sort it and then search it if you really want to, and do even more work than you need to. But we're going to go ahead and do a recursive version of linear search. Now, to motivate that, let's think of an array, right? Or let's think of the collection as an array, right? How can I divide and conquer it, right? Well, let's go ahead and take the idea of binary search, of looking at the middle element and asking whether or not if this is equal to K. If it is, what do? Yes, we will go ahead and stop, right? Output true. It does contain K. Otherwise, no. Then what do? Now, unlike binary search, where we can say, oh, well, if it exists over here or over here, depending on whether or not this is less or this is greater. Right? We can't do that with linear search because this is not necessarily sorted. So we're going to have to explore both of these regions. We need to recursively search the left half, and then recursively search the right half. All right? Help me. How do I do that? One part of thinking about thinking recursively is to think about the general case. If I started out with the whole array here, it would be A1 and AN. This would be the first element, and this would be the last element. That's one particular case. That's only the initial examination, right? What I want to do is I want to think more generally. I don't want to think of 1 and n. Let's think in terms of variables. Instead of 1, we'll call this r, or left, L, and we'll call this R for the right. A left index and a right index. Now, on that particular initial call, L will be 1 and R will be n. But on each other call, we're going to update R to be over here. We're going to update L to be over here. And then we're going to recurse. We're going to update our L's and R's as we go through. Okay? So keep that in mind. Always think about the general case. Take a specific example if it helps you to think about it, and then make it generic by replacing actual hard-coded values with variables. Okay? So how do we do this? Let's go ahead and write an algorithm here. I'll call it recursive or rec linear search that will take the collection A. It'll take these two variables that we've identified here, L and R, and then it'll also take the key K, because we don't want to lose sight for what we're searching for here. We actually want to, keep that in there. We're searching for K, and it doesn't change. What's the first step? Again, recursive algorithms, what's the very first question you ask yourself? You need a stopping condition. You need a base case. Where do we stop here? If I'm updating my left and right, left, right, left, right, left, right, then at what point do I stop? Here's my here's left, here's right. I move them in, move them in, move them in. When do I stop? When they're equal, right? If L is equal to R, then I'm looking at only one element essentially, and so I can return whether or not A sub L, or which is equal to R, so it doesn't matter. We'll return whether or not that is equal to K. Right? If it's equal, it returns true. If it's not equal, then it returns false. Okay. Otherwise, else, we need to recursively search the left half and recursively search the right half. So I guess I could check this one, I guess, right? Else, if A sub, I should have left myself some room here. How do I get to this element, by the way? So if it were 1 and n, then what's the middle element? N divided by 2, right? And then maybe take a floor, since that's not guaranteed to be an integer, right? Or rely on truncation if you're actually to program this. But if I've got L and R, I need to think more generally. How do I get the middle index here? The average, right? L plus R all over 2, and again, I'll take the floor of that. So if I want to call this M, then I need to take that. Now, this is what you do in pseudocode. As I try to cover in CS1 and maybe even CS2, I forget, you do not do that in practice. This is risking overflow. And so you would not want to do something like this. In fact, this bug existed in Java for 15 years. And nobody really cared about it because you'd have to have like an array of size, at least 2 billion elements or something to hit this overflow error. But it was finally fixed after 15 years, right? So I need to compute M, and it's simply going to be the average, L plus R over 2. Take the floor so that you've got an integer. And if A sub M is equal to the thing that we're looking for, then I will return, I guess. I'll use the same nomenclature up here. Return true. You found what you were looking for. Great. Otherwise, if you didn't find what you were looking for, then you need to recursively search the left half and recursively search the right half. So, else. And unlike binary search, like a recursive binary search where you would search one or the other, we actually need to search both of these. So what I'm going to do is I'm going to return a call to rec linear search on the left half. So A will remain unchanged, but if I want to search on the left half here, then L remains unchanged, but if I want to move my R over here, what's it going to be? Do I want to include M? I already checked it, right? So I will go M minus 1. And of course, K doesn't change. And I also need to recursively search the right half. So I can go ahead and put a disjunction here. This is either true or false. This is either true or false. You either find it here, or you could find it in both. Remember, we're not putting any There's no duplicates in here. Condition, that's not a condition that we put on this. If we're searching for 5, 5 could exist over here and 5 could exist over here. Right? I'll also rely, if this were a real programming language, I would rely on short circuiting so that if you do find it in the left half, then this doesn't get evaluated over here and it skips it. Right? Cool. Rec linear search on the right half. A. Now on the right half, L changes to M plus 1, R, and K. There we go. There's a recursive version of linear search. Normally you wouldn't do this, right? If you're going to do linear search, just it's a for loop. For I is running from 1 up to n. If you find it, stop and output it. Right? But here's a way of thinking recursively about it. How am I thinking recursively about this? I'm dividing it and conquering it. If I had 8 elements, one, two, three, 1, 2, 3. There we go. If I had 8 elements, the way that I'm dividing this essentially is into these 4 elements over here, just like merge sort does. Right? And I'm dividing it into these 4 elements over here. And I'm dividing those further into 2 elements and 2 elements. I won't draw it all, but then I'm dividing these into 1 element and 1 element until I get down to my base condition, in which case I only have 1 element to compare it to my key, and that's where my base condition is. Right? So all divide and conquer strategies will look something like this. You're dividing it up into 2 problems and until you get down to a small problem, and then you directly solve that problem, and you potentially have to combine the solutions back upwards. Is this recursive version any better than our regular old linear search? In other words, how many comparisons does this make? So what tool do we need to analyze a recursive algorithm? Remember that tool? The Master Theorem, exactly. What I'm going to do is I'm going to set up a recurrence here. I will let C sub n be the number of comparisons made by recursive linear search, RLS, let's say, on a collection of size n. Okay? So I need to get a hold on what C sub n looks like. Dang it, sorry. C sub n. What does it look like? Okay? Well, the base condition, when C sub 1, I make 1 comparison. All right? You can go ahead. The Master Theorem doesn't really care about this because the Master Theorem is all about asymptotics. But if you were to actually solve this, you would need, if 235. If you were to solve this, it's eventually going to be a non-linear, non-homogeneous recurrence relation. And so you would need the base condition here to be able to actually solve it and get a closed form solution of it. We're not going to do that, though, because we're just interested in the asymptotic behavior of this. I'm interested in applying the Master Theorem. So we make, how many recursive calls do we make in the worst case? 2. Right? So we make 2 recursive calls. Here's the first one, C sub something. How big is the input on this recursive call right here? If I originally had an array of size n, then how much am I cutting it into? I'm cutting it into 2 parts, right? And how big is each part? Roughly n over 2. Right? This is the first recursive call. This, likewise, is the second recursive call. Now, we might be off by 1, right? If there were 9 of them, then one would get we would cut out 1 to begin with, and one would get 4, and the other one would get 4. We're only interested in the asymptotic behavior. Right? Plus, what's the non-recursive work here? Right? Well, this is just a necessary for the control structure of the algorithm. It's the base condition that you quit on. Well, we're doing an addition, a division, we're doing a floor, we're doing an assignment. Pick any one of those to be your elementary operation if you want. Otherwise, there's also 1 comparison. Right? You're doing one comparison. So which one do you want? Do you want to do the addition, the division, the floor, the assignment, or the comparison? Comparison, because why? What would I label this anyway? The number of comparisons. So how many comparisons do you do non-recursively? One. Right. So altogether, this looks like 2c sub n divided by 2. All right, I'm just combining these two terms into 1 plus 1. Now remember the Master Theorem. Let me go ahead and write it down for you, and then we'll come back over to this. The Master Theorem. I think it's in the note set. If not, then you can always go back to my CS2 book, and it definitely is in there. Let t sub n be a recurrence of the following form: a t sub n divided by b plus f of n, where this corresponds to the number of recursive calls. Recursive calls. This represents how you're cutting the input size down, how much the input is cut. So in this case, it's going to be 2. We're cutting it in half. If you cut it into thirds or cut it into tenths, right, then B would be different. And then this is capturing the non-recursive work. And what the Master Theorem states is all you need to do is take A, B, and D here. Let f of n be theta or order, it doesn't matter, n to the d. If this is a polynomial, or if it can be bound by a polynomial, then we can say that t sub n is one of 3 things. Let me get my cases correct here. If I've got them. Okay, by memory. N to the d. If a is greater than b to the d, it's going to be n to the d log n if a is equal to b to the d. And it's going to be theta, again, or omega, n to the log base b of a. So it's still polynomial. If a is, oops, I think I screwed up already, b to the d, and this is less than. Less than comes first. There we go. All you have to do is look at the relationship between A, B, and D. Now, again, the hand-wavy interpretation of this is if you are making fewer recursive calls than you are doing non-recursive work, then you've got this solution. If you're doing roughly the same amount of recursive calls as you're doing non-recursive work, then you've got this solution. If you're doing more recursive calls than you are doing non-recursive work, then you've got this solution right here. All right? So now let's go ahead and go back over here, and let's identify A, B, and D. A is equal to, how many recursive calls are we making? 2. B, how much are we cutting it down each time? 2. And what about D? 1 is going to be theta of n to the what? 0, right? That's a polynomial. It's just a degree 0 polynomial. In other words, a constant. So D here is going to be 0. A versus b to the d. In other words, if I plug these in, 2 versus 2 to the 0. Is this greater than, less than, or equal to? It's going to be greater than. So by what case of the Master Theorem do we need to apply here? Case 3. So therefore, C sub n is going to be theta of n to the log base b of a. But log base b, log base 2 of 2 is equal to what? 1. So n to the 1 is simply just, don't write the 1, just order n. In other words, recursive linear search is still linear. It didn't bias anything. All right? Why didn't it bias anything? Let's go all the way back over here to the beginning. For a divide and conquer solution to provide a better solution, what do you have to do? you have to exploit some structure. Was there any structure that we could exploit? No, it wasn't sorted. We didn't say that with probability X, it lay in the left half or the right half or whatever. There was no structure that we could exploit. Okay? So now what we're going to do is we're going to look at several problems that do lend themselves to structure. And before I do this, how do we know that a problem has structure or not? As you'll see with a lot of these mathematical things that we're going to be looking at, it was just somebody writing down, exploring. They wrote down a bunch of identities, and okay, well that's equal to that, and that's equal to that, and they just kept rewriting and rewriting and rewriting. This is what mathematicians do. They try things, right? Just because a mathematician or a computer scientist or whatever, they publish a paper, there were 50 failed ideas behind that one paper, right? Because they tried a bunch of things and, oh, that didn't work out, that didn't work out. They tried it until they got that one idea where they found a structure. Wow, this is a discovery, right? They mined this thing for a structure. I can exploit that structure, right? And the first one that I'm going to show you is something that you're well familiar with already. Actually, no, sorry, let's go with this one first. Since we are familiar with it, let's look at the closest pair again. Closest pair of points. Remember, we're given a set of points. You're given which is x1, y1 in the Euclidean plane, x2, y2, ... xn, yn. Okay? And we want to output the two closest points according to Euclidean distance. Euclidean distance being the distance between 2 points P1 and P2 is square root of the difference of squares in their components. This is also called the L2 norm, right? y1 minus y2 squared. So there's the Euclidean distance, okay? So how could we apply a divide and conquer strategy to this as well as exploit some structure, okay? Well, I'm going to go ahead and visualize this. And for this, let me go ahead and take a pencil instead. Right? Here's the Euclidean plane. Yeah, okay. Is that showing up well? Well enough, right? So, and I didn't mean to draw this as an axis, or axes, but let's just go ahead and say that roughly we've divided it. In other words, there are given n points. Let's say that there are n divided by 2 points over here and n divided by 2 points over here. This is not necessarily the y-axis. I just drew, in fact, let me go ahead and redraw this so that it's, I'm just cutting it in half basically. If I gave you a bunch of points in the Euclidean plane, find me a y value such that half the points are over here and the other half of the points are over here, okay? Now the divide step here is to separate A into two partitions so that you have half the points over here and half the points over there. Conquer. Recursive, and I'll call these the left partition and the right partition. So over here this is left and this is right. Recursively find the two closest points in L and the two closest in R. Okay? I'm going to give the labels to the distances. Suppose that D1 is the min distance of points in L. In other words, suppose that I found these 2 points right here. These are the two closest points among these points over here. I'll call this D1. Right? Now, independently here, suppose that I found D2, these 2 points over here. These are the two closest points over in this partition. This is going to be the min distance of points in R. Right? Now, the naive way of looking at this, when you combine the solutions, again, divide, conquer, combine, is to simply take the minimum of those two, the minimum of D1 and D2. Does that solve the problem, though? No, why? What could I be missing here? When the minimum distance points, one of them happens to be over here, and one of them happens to be over here, right? That doesn't preclude these 2 points, say, where this distance is less than both D1 and D2, right? So how do I take care of that situation? Here's the problem. There may be 2 closer points such that one is in L and the other is in R. Right? So the naive way of combining these two things would be what? For each point in L, right? For each point, I'll call it Q in R, compute the distance from P to Q and compare it. If the distance is less than delta, remember I put delta up here, then update delta. Okay. Is that a good solution? N divided by 2 points over in L, N divided by 2 points over in R, and how many times do you end up computing the distance or making this comparison? N divided by 2 times N divided by 2. This is going to be, well, I don't care what the constant out front is, 1/4. It's going to be order N squared. Right back to where we were. Right? And why didn't this work? Same reason that linear recursive search didn't work. We didn't exploit any more structure than what was already there. So let's not be naive about this. Let's redraw this picture and think about this for a moment. Okay? And I will go ahead and draw the partition with a different color. There we go. So forget all the points for a second, and let's just say that we've got D1 and we've got D2 over here. All right? And now think about a point over here in the left partition. Do we need to compare it to a point way over here? No, why? That's way larger than either D1 or D2, right? So we don't need to compare it to far away points. We only need to compare it to, say, closer points, right? Points that are closer to this partitioning over here, right? Now, how many points could that be? Let's zoom in on this. All right, I'm going to draw it down here. Suppose this is our point over here on the left-hand side, and I'm going to draw it so that it is nearly sitting on top of that thing, right? That it is epsilon close to this partition over here. Now, if I've got delta, which is going to be the minimum of D1 and D2, how far away from from this point over the partitioning separation line do I have to search? Only delta distance away. What does that look like? Well, yeah, a circle or a semicircle, since we're cutting it in half, right? A hemicircle? We don't say that, right? We say semicircle, right? So let me go ahead and draw that semicircle right here, such that this radius right here is delta. Okay? In other words, if there is a point that is closer than either this or this, that in other words, there's a point that's closer than delta, it can't be further away. Any point over here, I can ignore those points. Right? Now, how many points can I fit into this half circle right here? I don't know. I've never actually been able to think about this geometrically. There we go. Thank you. I've never thought about this in a formal geometric sense, but let me go ahead and draw a half circle here of delta radius, delta radius. And we could fit a point over here, right? And that's going to be exactly delta away. And since it's epsilon over on the other side, we do have to consider that point. I could fit another point up here, right? That's just on the other side. I could fit another point over here, right? Now, if I put those maximum distance points away, could I put yet another point right here? No. Why? What's the distance? Now, this point and this point lie on the same partition. Tell me about their distance. That's smaller than a circle of radius delta. So what is this distance right here? This is strictly less than delta. So if there had been a point over here, then we wouldn't have said that these were the two closest points over here. We would have said these are the two closest points because it's even smaller, right? So fit as many points in there as you want. If you want, and if you are reading Leviton, or if you're looking at some of the videos online that present this problem, they don't look at a circle. They look at Manhattan distance, and they try to simplify it so that there are these boxes that are delta away. All right, they don't even want to look at the geometry of a circle. They'll look at these boxes and then say, okay, there can only be one point in each of those boxes. I like looking at a circle because it tells me that there are at most 4 points, right? Because the other point over here is on the other side of the partition, and so all we need to do is look at most 4 points or something like that. In other words, we don't need to do this naive algorithm over here. All we need to do is, for each point, I'll say P in L, compare P to at most, say, 4 points in R. I'm not going to write a more formal algorithm than this, because this gives you the answer. How many points are there in P? N divided by 2. But you're only comparing it to a constant number. Now, if your constant number is 4, 5, 6, 7, 8, it doesn't matter. Who cares, right? It's constant. I'll call it K. Right? So we've got that there are going to be K times N divided by 2 comparisons. Tell me about the asymptotic behavior of this now. K is a constant, 2 is a constant. What happens? We only have a linear amount of work instead of a quadratic amount of work, because we are exploiting structure. We're exploiting geometry. We're reasoning that we don't have to compare it to every single point. We can reduce our workload by exploiting this geometric structure here, the distance. Okay? Now, let's come up with a recurrence on this one. Let C sub n be we'll do comparisons. Number of comparisons made by this algorithm by, I'll say, divide and conquer, closest pair. All right. Now, we cut it into 2 parts, so we're going to have to make 2 recursive calls. How many points are in each one of those recursive calls? N divided by 2. So already this is looking familiar. This shows up all the freaking time. Right? How much non-recursive work do we have to do if we exploit that structure? We only have to do a linear amount of work. So I'll go ahead and just say, well, it's n. Again, k times n divided by 2. Go ahead and put a constant out front there if you really want to. Right? It doesn't matter, because when you apply the Master Theorem, A, the number of recursive calls is 2. B, the amount that you cut it in half by each time is 2. You're cutting it in half each time. And D is going to be 1, because this is a linear function. So A versus B to the D. 2 versus 2 to the first. They are equal. Right? So case 2 of the Master Theorem applies. And let me go ahead and bring that back. case 2 of the Master Theorem applies, and we've got that it's theta n to the d log n. So it's going to be theta n to the d, but d is just 1, so it disappears, log n. Right? That's much better than, we call this quasi-linear. It's not exactly linear. That would be linear. It's got this logarithm, log factor there. But logarithms grow so slow that for all intents and purposes, it might as well be linear. Right? Now, if you remember the demonstration that I gave you on Monday to start us out with, I wrote a C program that we calculated that it would take weeks, or minutes, hours, days, weeks, years for even moderately sized inputs. Those moderately sized inputs now become a matter of, instead of hours, weeks, hours, days, weeks, and years, they all get shifted down by an order of magnitude. Now, instead of years, you might have to do a few minutes or hours of computation instead. Okay? Again, exploiting structure. Every single algorithm out there, every single efficient algorithm that you develop is nothing more than mathematics. The mathematics of finding a structure and proving that structure and then exploiting that structure. That's all algorithm development really is you're not thinking about loops all the time. You're not thinking about backtracking or whatever. You're not thinking in terms of coding with algorithms. You're thinking in terms of mathematics, and you're thinking in terms of what structures can I exploit. Same thing with data structures, by the way. In 156, I typically cover, all right, well, here's a list, and here's a general graph. It doesn't have much structure, and so we've got very inefficient graph algorithms. What if we say that it's acyclic? Now we've got a tree. What if we also say that it's oriented downward and we've got parent and child relationships? What if we also say that it's oriented left to right? What if we also say that there is a structure to it, that there are keys stored in here, and every key over here is less and every key over here is greater? More and more and more structures allow you to exploit that structure and use them as data structures or use them as efficient algorithms, right? To make things that were infeasible feasible. Here's another example that you probably have seen before. Or not directly seen before, but I'm going to motivate this by asking you to write me some Java code or C code, whatever you want. So what I want to do is I want to compute the following. Compute a to the n mod m. Right? So in other words, my inputs are going to be, say integers, it doesn't really matter, a, n, and m. Right? Write me some Java code to do this. I'll get you started. We'll say that they're all integers. Int a, n, and m. And they get set somehow. Who cares? Let's go ahead and create an integer here called r for result. In fact, let's just go ahead and call it result. Right? We're not paying by the character. Right? So int result. And in fact, maybe I should have set that equal to something initially. We'll come back to that. Now, 99 out of 100 CS1 students, CS2 students will probably write the following code. Right? Does anybody want to suggest that, the naive code? It's just a simple loop, right? For int I equals 0, I is less than, say, n, right? Because what we're going to do is we're going to go a times a times a times a times a. How many times? Well, we're going to do it n times here, so where should I start the result? 1, I plus plus. And what we're going to do is we're going to set result equals to result times a, and then you can take the mod. What is mod in Java, most programming languages? %m. You can do it every single time to avoid overflow. You can keep it small. Right? In fact, you can even assume that a is small, say 7, and that m is small, say 13. Right? But don't assume that n is small. Right? This will get the job done. This actually works. Right? This code will work. And if you put it in for 7, 13, and maybe n is maybe 100, or let's say that it's 77. Right? Let's say that n is equal to 77, right? Because that's the example that I've got in the notes. How many multiplications do I end up doing? I do it for I being 0, 1, 2, 3, 4, all the way up to n minus 1, because it's strictly less than. So the number, again, say that a is, we don't care, 3, and m is 7. They're small. N is a little bit larger, but it's still small, only 77. How many multiplications do you end up doing? Number of mults. How many? 77. All right. Okay. What if I said that n is 1,512,000? There we go. So how many multiplications now? How many iterations would you go now? 1 million. I'll just go 1 million plus. Right? Dot, dot, dot. What if I just said it was n period? How many multiplications? N. So this is going to be, oh, it's linear. Is it linear? Okay. Oh, we'll answer that question and come back to it. Suppose that I said that n was a large number. 2 to the 1024. About. That's kind of a large number, but is it really? How many bits are required to represent that n? Hint, 1024 bits. Is 1024 bits large input? No. This is routinely done with cryptography. If you connect to Amazon, all right, you are doing SSL with secure socket layer where you are doing cryptography back and forth. You are doing mathematics with numbers this large every single second. But if I'm doing this algorithm to do this kind of stuff, how many multiplications do I do? Well, we said that if it was 77, we did 77. If it was 1 million, we did 1 million. If it's 2 to the 124, or to 1024, how many multiplications do we do? Several universes full of multiplications. Right? Remember, did anybody ever look that up? How many atoms are in the known universe? Or observable universe? No? I think it's 2 to the 100. So we're doing 10 universes of computation here. Right? Do you think that that's going to actually execute? No. Not in your lifetime, not in the universe, not in 10 universes' lifetimes. Is that going to execute? So, what was our problem here? N is the input. Again, that 5-step process. The input is n. 2, what's the input size? How many bits does it take to represent n? Well, in this particular case, it took 1024 bits. Over here, it took about, I want to say 10, 12, 13, let's say 16 bits. Right? Over here, it would take about 9 bits. Right? So, in general, the number of bits to represent n, which in general is what? Log base 2 of n. Right? Just like log base, what is one interpretation of log base 10 of x? The number of digits it takes to represent something. Right? What's log base 10 of 1,000? 4. Is it 4? It should be 3, right? Yeah, 3. So plus 1 gives you the number of digits to represent that thing. Right? This plus 1 gives you the number of digits, but we ignore plus 1 because of asymptotics. So our mistake here in assuming that this was linear was not correct. N is not the input size. The input size is log n. So if we've got, let me go ahead and rename this, right? The input size is going to be n, big N. So this is not, this looks linear, but it's actually equal to 2 to the big N, where big N is our actual input size. Does that look linear to you? Nope, that is exponential. All right? So this solution is terrible. We don't want to do this naive solution. We want to exploit structure. let me give you a divide and conquer approach. Suppose that I want to, and to make this nice and even, let's go ahead and suppose that we want to compute a to the 32nd. Okay? How could I rewrite that algebraically into two multiplications instead, two numbers instead? A to the 16th and a to the 16th. If I multiply these two numbers together, that's one multiplication, and I get a to the 32nd, right? Well, there's nothing to stop me from dividing again. A to the 8th, a to the 8th, a to the 8th, and a to the 8th. Right? Let's go ahead and divide it again. A to the 4th, a to the 4th. And I won't write the entire tree here. I'm not that good of an artist anyway. And it'll all look bunched up together anyway. All right? I will draw a little bit more of the tree over here. A squared, and a. Now, imagine this entire tree has been fully rendered and fully written out. What does this solution correspond to? This solution corresponds to going across every single leaf and multiplying this leaf with this leaf with this leaf with this leaf with this leaf. Right? How many leaves are there going to be here? 32. So you end up doing 32 multiplications. Right? If you start out with the first multiplication of 1 times a and then dot, dot, dot. If you initialized it to a, then you could get away with skipping one of those multiplications. But skipping one is not worth it. How could we exploit structure? Oftentimes I will present the Fibonacci, the recursion using the worst best example that you can show, the Fibonacci sequence. Because if you show the recursive version of the Fibonacci sequence and you draw out this big, huge, giant tree, you start to notice a pattern. When I try to compute the Fibonacci of 20, Fibonacci of 10 is computed an exponential number of times and recomputed and recomputed and recomputed. Right? That's why you don't do that in recursive version. Instead, you use something called memoization. That we hopefully you remember that. Otherwise, we will revisit that along with dynamic programming, and you reuse that computation. If you compute the 10th Fibonacci number, store it and save it and remember it, so that you don't have to recompute it every single time. Do you see a pattern here? Is there anything repeated here? How many times do I need the value of a to the 8th? 1, 2, 3, 4. A to the 16th is repeated twice. If I go down here and I draw all of this out, a to the a squared is going to be repeated 16 times. Right? Don't do that. Don't recompute things over and over again. Instead, what I'm going to do is I'm going to follow this tree, this computation tree, from the bottom all the way to the top. A times a gives me a squared. Right? That's this part right here. Now, once I've got a squared, I can eliminate everything over here. How could I do that? By computing a to the 4th. In other words, take this a squared, square it again, and I get a to the 4th. So let's keep a track here. How many multiplications am I doing? 1. This is a multiplication. Square is just multiplied by one multiplication. 2. Let's square this again. Bring this over here. A to the 4th squared. That's only one more multiplication, so there's 3. And that gives me a to the 8th, right? Multiplication. Or write it out, and then you add the exponents. Do that again. A to the 4th, or a to the 8th, excuse me, squared. That's the 4th multiplication. And this gives me a to the 16th. Okay. Do that again. A to the 16th squared. There's my 5th multiplication. And that's going to be a to the 32nd, which is exactly what I wanted. I didn't have to do 32 multiplications. How many multiplications did I end up doing? 5. Right? I didn't have to do this entire exponentially sized computation tree. All I did was one branch, right? Because, again, this is going all the way up here. Right? All I had to do was one branch. Now, you might ask yourself, well, wait a second. What if I wanted to do a to the 77th? Right? This is great if you are only wanting to exponentiate it up to a power of 2, right? 1, 2, 4, 8, 16, 32. Tell me about a to the 77th. How could I rewrite that? A to the 64th times a to the, well, here I'll go at 13. And I'll break it up even further. A to the 64th, that's a power of 2. That conforms to what I was developing over here. How can I break a to the 13th up? A to the 8th, and here I will do it all in one line now. A to the 4th, and a to the 1st, right? Add up those exponents, and what do you get? 77. You only have to compute powers of 2, right? And so all you have to do is compute this. All you have to do is repeatedly square things, save off the ones that you need, right? There are other ones that are here, like a squared. Well, that's not here, but I didn't need it. Likewise, a to the 16th. That's here, but I didn't need it, at least for this, and a to the 32nd. I need them temporarily, but I don't need to bring them all the way through. Right? And that's the idea behind an algorithm called repeated squaring. Right? Yeah, okay, good. We're good. Okay. And I'll come back to that. Okay. So my input here is going to be those numbers that I had before, a, n, and m, and with n being in binary. Of course, everything is in binary in a computer, but except for those pesky like ternary computers that exist out there, and that is somewhat of a joke. But there have been digital analog computers that were not base 2 in the past. Are there any such things anymore? I don't think so, but at least not in wide usage. Everything's digital now. Everything's binary, right? But I'm giving n binary labels here, that it's going to be a k-bit number, okay? So just because I need to work with it. My output is going to be a raised to the n mod m, okay? So I'm going to store off the term a to begin with, because it's kind of like what I did with the other one. I started the other one at 1. I need to determine, do I need to start at 1 or do I need to start at a, based on this lower order bit here. Right? If that bit is 1, then the term that then my product, I'll start that out at a. Otherwise, I'll start my product out as 1. In the naive solution that I gave you before, I started it out at 1. Again, it's just whether or not you need a to the 1st. Right? This is going to correspond to a to the 1st, a to the 2nd, ... a to the 4th, all the way up to a to the 2 to the k. Right? But that's just for to keep that idea in your mind. Right? Then I'm going to go with a for loop for I running from 1 up to k. In other words, I'm going to run over all of these bits. Okay. I will square the term times term. And I can also take the mod of this. It works out mathematically just to keep it small. If you don't want to do that, fine, but it's pseudocode. You can do it later. In real code, of course, you would want to keep it small to avoid overflow. And what this is doing is this is simply just taking a to the, well, whatever it might be, and we're squaring it, just like I did over here in this demonstration here. I took the last term, I squared it, took the last term, squared it, squared it, squared it. Right? And I checked to see, what does this bit look like? If b sub I, right, is 1, then I need to include that in there. This bit was 1, so I needed to include it. This bit was 0, so I don't include it. This bit was 1. I'm going 1, 2, 4, 8, 16, 32, 40, 64. I need to know whether or not I need to include it in this result right here. And that's all just based on the bit. If the bit is 1, yes, you do need to include it. So product is going to be product times the term. And then again, mod m. Otherwise, if the bit is 0, forget about it, but still square the term. And then output product. That's it. So questions on that before we give an example? No? Okay. I'll leave the bottom up here. All right, so that we can run through this. Let me go ahead and compute 12 to the 26 mod 17. Now, I'm fairly certain that Wolfram Alpha would do this, but does your typical handheld calculator do something like this? Does anybody have their TI-82 on their desk and want to try it? Let me know. Let me know if it does that. All right. So A is 12. N is 26, and let's go ahead and convert that to binary, and M is 17. So help me convert 26 to binary. So it's going to be 16, 8, no 4, 2, and no 1. All right, this is 26 in binary, right? Let me check. 11010. Yep. All right. So there's my input. What I'm going to do is I'm going to keep track of I, the term, and the product. All right. So here, 26 in binary is going to be 0, 1, 0, 1, 1. There we go. And so I here is, well, this is the initialization phase. I'm working this direction, by the way. This is 1, 2, 3, and 4. There we go. I'm going to be working this way because I'm working in the least significant bits up to the most significant bits. Otherwise, if I worked in the other direction, then I would have to pre-compute n to the 64 or a to the 64 and then work backwards down. I'd have to store everything off, and that's not what I'm going to do. So let's simulate this algorithm here. The term is going to be a, so a in this case is 12. Then the lowest order bit, is it 1 or 0? Well, it's 0, so what do we end up setting the product to? 1. Now let's go ahead and go into this loop. There we go. Sorry, that was off. So, sorry, this should be k, I guess. Well, it doesn't, yeah, k. That's what I put up here. So what are we going to do? We're going to square the term and then mod out by 17. So what's the term? 12. 12 squared is 144. Mod 17 is going to be, might have to help me here. 26, so 9? Nope, 8. I was off by 1. 8. There we go. That's 12 squared mod 17. Right, so 144 mod 17. And if those of you with your calculators, please let me know if I'm making a mistake here. Right. Otherwise, then we look at this bit. This bit is 1, so we take the product, 1, times the term, and then mod out by m. So 1 times 8, that's easy. Don't worry about your calculators. I can do that one. 8 mod 17, of course, it stays 8. Okay. Next iteration, we square the term again. That's 8 squared, which is going to be 64. Mod 17. 13? Yep, great. And is the bit 1? No, it's 0, so we end up carrying over the product. It's unchanged. There's no else condition here. Okay. Next iteration, we square the term, so 13 squared is going to be 169. mod 17. Oh, so that should be easy. It's only one less than 170, so it's going to be 16. Oops, sorry, 16 over here. Right? Yep. And the bit is 1, so we end up multiplying these together. 8 times 16 is going to be 124. Or 124, no. 128, sorry. Mod 17. Help me out on that one. Anybody do it in their head? 34, 0, right? Or no, it's 9. Sorry. I kept thinking 34. 34 is not a power of 2, so it's 9. Next iteration, 16 squared is going to be mod 17. I have no idea. I'm going to have to appeal over here. It's 1. Right? And now this last bit is 1. Of course, the most significant bit is always going to be 1. Otherwise, you don't have leading zeros. 1 times 9 mod 17 is simply going to be 9. We multiply those together to get 9. So this is going to end up being 9. Tell me, those of you with TI-82s or whatever you've got, were they able to do that? Oh, nobody tried it? Okay, all right. Typically the cheaper calculators will have overflow immediately. The graphing calculators will certainly, hopefully, be able to do this using this kind of an algorithm here. Right? Before we go on, how much more efficient is this? All right. So this is all initialization and setup. You can choose whatever you want in here. This multiplication, or maybe both multiplications, this modulus operation here, right? Whatever your operation, if you choose for your elementary operation right here, how many times is it executed? This is order k. Well, what is k? K is the number of bits. Number of bits of n. K is equal to what? How many bits does it take to represent n? Log n. Right? So this is it logarithmic? Is it like binary search where it's sublinear? No. The input, again, if you go through your 5-step process, the input is n. What is the input size? It was, we'll call it big N here. It's log n. So therefore, remember from 235, 3 dots, therefore, this is going to be order, or theta, let's say, n. It's linear. Right? Where n is big N here. That's logarithmic. K is log. So plug that in, and that you get that it's linear. Right? Which is not as good as, say, binary search, but binary search is only sublinear because it gets to throw away half the input every single time. When you do mathematics and you need to multiply stuff, you don't get to throw out the input. If you have this number and you want to multiply them together, you don't get to chop this number in half and throw it away. You lose precision, right? So you have to at least look at the entire input. Right? And by the way, speaking of multiplications, remind me, how did you learn multiplication in, say, grade school? Actually, before we get that, that's okay. I don't need to give you more astronomical numbers or anything. All right. Let's see. Not this one, not this one. How did you multiply in school? I'll give you 2 numbers here. Let's go back to grade school. All right. Multiply those numbers together. Help me out. 1 times 7, so 7. 1 times 4. So keep count here. There are 2 multiplications so far. 47. Now what? All right. Now plus 5 times 7, which is 35. Carry the 3. 5 times 4 is 20. Carry that down, 23. right? Is that correct? Okay, what is, so I did a multiplication here and a multiplication here. That's 2. Is that a multiplication? Did I have to multiply by 10? Is it? If I want, what's the difference between 2, 3, 5 versus 2, 3, 5, 0? Right? You multiply this one by 10. Is there an easier way of doing it? Do you actually have to multiply to get that over? There's implicitly a point here, right? And implicitly there's a 0 here. 2, 3, 5, 0.0. Is it a multiplication if I simply just take this point and float it over here? Is that a multiplication? No. That's why we call them floating point numbers, right? Because if there's a point here, and you can, if you, it's just a shift, right? In computers, if you want to multiply something by 2, x times 2, what's another way of doing that? In most programming languages, here let's actually write some Java code. Int x, and then dot dot dot. X is equal to x times 2. What's another way of writing that? X times equals, yes, but what's another way? In fact, what's your compiler going to do? It's going to see multiplication by 2. I'm not going to multiply this. I'm going to, oh, okay. It could do an addition. What's even more efficient? Here's a number, 7 times 2. What's 7 in binary? 1, 1, 1. This is going to be 14. What's 14 in binary? 1, 1, 1, 0. Right? Verify that, right? 7, 8, 4, 2. Add those all together. What do you get? 14. What did you have to do? Take this and shift it over. Right? One way that you can do this in most programming languages is to shift it by 1 bit. Right? This is, in fact, it was what your compiler is going to end up doing. Your compiler is going to see multiplication by 2. No, I can do better. I can do better. I'm just going to shift it over by 1. Right? All it is taking your bits in your register or your in memory or whatever, shifting them over, and potentially there's overflow, of course. If you multiply 2.147 billion by 2, there is going to be overflow, and then it overflows into the sign bit, and now you've got a negative number, right? That's why you get overflow like that, right? So this is not a multiplication. This is super cheap. This is a shift, right? By the way, what if you want to divide by 2? You can go the other way. Right? What if you want to cyclically shift things? Sometimes, in some programming languages, you can do this. What if you want to multiply by 4? Shift it over by 2 bits instead. What if you want to multiply by 8? Shift it over by 3 bits, et cetera, et cetera. Right? So the thing to get out of this is that shifting it does not cost you a multiplication. Your grade school multiplication techniques here only cost you 4 multiplications. Right? Can we do better? Can we divide and conquer this and exploit some structure? What I'm going to do is I'm going to rewrite everything. 47 times 51. I'm not going to do it the old grade school way. What I'm going to do is I'm going to split it up. I'm going to divide it into single numbers. The 4, the 7, the 5, and the 1. 4 times 10 square, 10 to the first. I'll leave it as with a 1 there. Plus 7 times 5 times 10 to the first plus, oops, I meant to do like that, sorry. And I'm doing it in pen, so I can't erase it, sorry. Right. Now, what do you see here? You see A, B, C, and D. right? So let me rewrite this as A plus B times C plus D. Now, we've graduated a little bit. Now we're in middle school mathematics. How do I go about expressing this? How can I distribute these things? What is that called? What is that rule called? Oh, yeah, it's distribution, but then the what do you call it? The acronym, the mnemonic device. What is it? FOIL. First, A times A, or A times C, plus outer, which I don't want to screw this up. A to D. So A. Oh, did I? No, I want AC first. Then AD. Inner. BC, right? The two inner. Then last, plus BD. Okay. Now let me go ahead and shift this. So I've got these two things right now. Right? FOIL allowed me to do this. Okay. So by applying FOIL, am I getting away with any fewer multiplications yet? How many multiplications are here? 1, 2, 3, and 4. All right. All right, so it didn't get anywhere. But again, like I said at the beginning, these things are usually discovered by mathematicians just writing and rewriting stuff. Okay? So let me go ahead and group these two, right? Yep, AD and BC, right? And what does that equal to? Let me rewrite this. AD plus BC. Well, it's equal to, if you want to cover the original, A plus B times C plus D. And then if I take these two onto the other side, then I subtract them, AC and BD. Right? Now, how many multiplications are there now to compute this part right here? There's 1, 2, and 3. Right? So let's go back up here. I would need to compute this, but guess what? I can reuse it. I need to compute this, but guess what? I can reuse it. I only have to compute it once. And now I don't have to do these two multiplications. All I have to do is perform one more multiplication and two additions. And I cut down 4 multiplications. I cut it down to only 3 multiplications. Pretty cool, right? All it is middle school algebra. So how can we exploit this now? Again, these things are thought up by mathematicians just, oh, rewrite this. Oh, hey, you know what? 4 multiplications, I can get away with only 3. Does that help me? Right? And the answer is yes. All you need to do is take a general A times B and split it up. Suppose that you've got, let's say that A is equal to, you split it up in half, right? A1 times 10 raised to the n divided by 2. Now they're n-digit numbers, right? They're not just 2-digit numbers anymore. Let's suppose that we've got these very large n-digit number times an n-digit number. Instead of doing n-squared operations, we're going to split it up into 2 n by 2-digit numbers. And B is going to be B1 times 10 to the n divided by 2 plus B0, right? Here, let's visualize this first, right? A is going to end up being, say, there are n digits, or if we wanted to consider it in binary, they're going to be bits or bidgets, right? That's what they were originally called. And this is going to be A1, and this second part here is going to be A0. And likewise, we break up B into 2 n by 2-digit numbers. Right? This becomes, and then again, is this going to cost us anything? This multiplication by 10 divided by 10 to some power? Nope, it's just a shift. you shift it over. And if this is in binary and base 2, then you just shift it over by multiplying by 2 instead. Right? So we're going to cut these down into 2 numbers, and if we want to multiply them together, into 4 numbers, excuse me, then we apply the FOIL rules. A times 10 to the n divided by 2 plus a naught multiplied by b1 times 10 to the n divided by 2 plus b naught. Right? And again, if we make our FOIL rules here, this is A, this is B, this is C, this is D. Maybe I should have gone with X and Y here, sorry. Not to be confused with A, B, and C and D of the FOIL rules. But this will end up being A1 times B1 times 10 to the, now what happens when I combine these two? It's going to be 10 to the n, right? Plus FOIL O, it's going to be A1 times B1, or B naught, times 10 to the n divided by 2. Right? This one times B naught. Then I of FOIL, A naught times this thing, B1 times 10 to the n divided by 2. And then plus, the last one would be A naught times B naught. Right? And doing our rearrangement that we did before, this is simply going to be, we can take this thing and do it in terms of this and the outer two values here. So it's A1, B1, 10 to the n plus A1 plus A naught times B1 plus B naught minus A1, B1, that first one right there, minus A naught, B naught, that last one right there. And then I've just factored out, to simplify everything, factored out the 10 to the n divided by 2 plus this one right here. Right? That suggests that we can get away with 1, 2, 3 multiplications, reuse this one, and reuse this one. Right? So we've divided by taking two n-digit numbers, divided them out into 4 n divided by 2-digit numbers, and we've come up with this equation right here that we now have to actually multiply everything, subtract everything, and add everything together. What we end up doing is, well, now you need to multiply if we started out with, say, 16-digit numbers, we cut these down. These are now 8-digit numbers. How do we do this multiplication? We cut them down into 4-digit numbers. And then we cut those down into 2-digit numbers. And then we cut those down into 1-digit numbers, at which point we take 1 digit times 1 digit. You can't go any further than that. So you multiply them together, and then you conquer by passing those all back up. Okay? Now, that's the idea. With the last 5 minutes here, let's think about whether or not that's better. Originally, if I have 2 n-digit numbers, then the naive approach, we'll call it elementary school method, would have you be doing, here's A1, A2, A3, dot, 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 AN, B1, B2, B3, dot, 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 BN. And if you multiply these together, how many multiplications would you end up doing? Well, you'd take Bn and you would multiply it with n times. You would take Bn minus 1 and you multiply it n times. So you would end up doing altogether order n squared multiplications. All right? It doesn't seem that bad, especially if we've got small digit numbers. Again, in a computer, basic integer can only represent up to 2.147 billion, so just go ahead and do it, right? 32-bit numbers, 64-bit numbers, there are actually circuits that will do it efficiently, and there are other ways of doing this in circuitry that we're not going to talk about here because it's not a circuits course. But carry ahead, look ahead adders, things like that. But what about this method that I just showed you? It's called the karatsuba multiplication, where you split the input in half, recursively make, how many multiplications did I make again? 3 multiplications. And perform 0 non-recursive multiplications. What else did we do? We did shifts, right? We did n shifts, n divided by 2 shifts. So perform, say, 2 shifts. These are free. And how many additions and subtractions did we end up doing? 1, 2, 3, 4, 5, 6. We ended up doing 6 additions. So one way of looking at this is we kind of blew up the number of additions. But additions are way less expensive than multiplications. So at the expense of some additions, additional additions, we're getting away with fewer multiplications. Is this better? Right? So let's go ahead and set up a recurrence. M sub n is going to be the number of multiplications by karatsuba on 2 n-digit or bit numbers. All right? Well, I make 3 recursive multiplications on how big is the input size? Where it's cut in half. So the recurrence would look like this. And I perform how many non-recursive multiplications? M, I'm capturing the number of multiplications. If you want to, you can go ahead and go with A to capture the number of additions, or S to capture the number of shifts. But the whole reason of me doing this is to cut down on the multiplication, so that's what I'm interested in. Right? How many non-recursive multiplications do I make? 0. So by the Master Theorem, A is 3. We're making 3 recursive calls now. B is 2. We're cutting it in half each and every single time. And D is equal to what? That's bounded. That is a polynomial. It's bounded by a polynomial of degree 0. So 3 versus 2 to the 0, which is equal to 1. This is strictly greater. Right? This is case 3 again, which tells us that M sub n is theta of n to the log base b n to the log base b, which is 2, of 3. Now, does anybody have their calculators out? There's still nobody decided to do that. Although I'll have to look it up then. 1.58. 1.58. All right. Log base 2 of 3 is 1.58. ... All right. It's irrational. It's not going to terminate there. Right. So is that better? Asymptotically, is it better? N squared for the naive approach. Is that better than n squared? Absolutely. Is it better in practice? Think about what we would have to do to implement this. And I'm talking about implement this in binary. Of course, you wouldn't want to implement this base 10 because you'd be converting between binary and base 10 the entire time. Right? There's a lot. You end up paying a lot of overhead for your recursion. Your numbers would have to be billions and billions of digits for you to even consider the trade-off of this divide and conquer approach. There are much better ways of doing this. I'm not going to go into them, but in the last few minutes here, I will mention some of them. I think Karatsuba was I think he was Russian. He came up with this in 1960. And then they were always looking for better ways of multiplication because back then, digital computers, they were digital, but they were all like vacuum tube computers, right? So super slow. And so they were always looking for better and better ways of doing this stuff. Toom and Cook came up with a better algorithm in 1963 that cut it down to n to the 1.465 or thereabouts. Right? But the real breakthrough was in 1968, where we came up with the German speakers can correct me on my pronunciation, Strassen. They came up with the first fast Fourier transform. And they cut it down to almost quasi-linear. N log n of log n. So that's a log of n. And there are three terms here that you can distinguish. So in other words, they cut it down to the polynomial down here to a linear term. And there's still a logarithm here. Of course, the best possible solution would, of course, be if you could find a way of multiplying two n-digit numbers together that's linear in both those, that'd be perfect. Right? Again, you can't ignore digits. If you ignore digits, then you've already said, I'm okay with losing precision. Right? And you can do that if you want, and then you can throw out half of the lower order digits and then get it down as much as you want. But if you want accuracy, then this is the best that you can do. Between then, Fourier, also German, I think, maybe, I don't know, 2007, improved this to order n log n 2 to the log star, which is the iterated logarithm. There we go. So it's almost n log n, which is going to be competitive with, say, sorting algorithms and stuff like that. But there's this annoying little thing over here. It's much better than log n. What this is the iterated logarithm function. So take a number, x. How many times do you have to take the log of that number until you get to 1? Right? So 64. If I take log base 2 of 64, what do I get? It's a 6. So that's one iteration. What if I take the log base 2 of 6? I will get 2 point something, something, something. I don't know. What if you do that again? Log of 2 point something, something, something. Well, this is 1 point something, something, something. If you take log of 1 point something, something, then you get down to below 0. Below 1. Sorry, not 0. So the iterated log, 1, 2, 3, 4 applications for 64. This is super slow growing. You can get up to 1 billion here, and you're still only in single digits, right, of value here. So this is extremely slow growing. Right? And it's just a factor that comes up with in the analysis of his idea. All of these are the same basic idea. How can you break something down and divide it and conquer it and exploit structure? The structure that the fast Fourier transforms exploits are called convolutions. And it's something that we're not going to get into this course. But really, really, really cool stuff here. Every single algorithm is like that. Exploit some structure. Identify a structure and exploit it so that you be more efficient.